Hello everybody here in the room, and greetings to the people following from the streaming platform. Welcome to the 2022 Econ Seminar Series. It's an honor and a pleasure for me to introduce Dr. Lu Xu. Lu is a research scientist at NOAA Chemical Science Laboratory. He got his PhD in chemical engineering from Georgia Tech under the supervision of Sally Ng. After graduation, he worked as postdoc with Professor Paul Wimberg at Caltech, and he will start as an assistant professor at the Department of Energy and chemical engineer at Washington University in St. Louis in the summer of 2023. Congratulations. His research focuses on investigating the sources and information mechanism of air pollution. He developed detailed chemical mechanism for predicting air quality and developed advanced instrumentations for characterizing atmospheric composition. His research approach involves laboratory study, field measurements, and instrument development. And today he's going to tell us about oxidative chemistry of atmospheric trace species in the Anthropocene. For the folks following via streaming, I want to remind you that you can type your questions at any time during the talk down in the window down below where you're looking at the video. And I'm going to read those questions at the end. And for the people present, I'm going to have a microphone and walk around gathering questions. With that, please help me welcome Lu on the stage. And take it away.
Thank you. Thank you for the introduction and invitation. Can you hear me okay? Cool, thanks. I have been to this auditorium several times, but this is my first time facing this direction. Yeah, so my name is Lu. I came to US in 2011 to pursue a PhD degree at Georgia Tech. Since then, my research has been focusing on atmospheric chemistry and air quality. And today, I would like to take this opportunity to summarize some of my major findings in the past 10 years and share some thoughts on my future research. So I'm interested in air pollution because it's a pressing environmental issue around the world. Before moving to Boulder, I spent about 4 years near Los Angeles, and I can testify that the air quality in Los Angeles is very bad. Before coming to the US, I grew up in China, and the air quality is very bad when I was a child, and the air quality has improved substantially in the past few years. But air pollution is very bad. Air quality still happens from time to time. And air quality is also a common issue in many other countries as well. We care about air pollution because air pollution is bad for our human health. World Health Organization estimates that air pollution, mainly ozone and particulate matter, account for 1 in 8 deaths worldwide. And what are these air pollutants, and where do they come from? As a chemical engineer, I like to describe our Earth's atmosphere as a giant reactor. The inputs to this reactor comes from very diverse sources, such as motor vehicles, power plants, wildfires, vegetations. And these sources emit a multitude of different species into the reactor, such as nitrogen oxides, NOx, sulfur dioxide, SO2, and volatile organic compounds, VOC, and many others. And these emissions undergo very complex chemical reactions in the reactor and produce even more pollutants. For example, ozone is produced in the atmosphere through the reactions of VOCs and NOx. Particulate matter, also known as PM or aerosol, is a complex mixture containing hundreds of thousands of different species, which can either directly emitted from a source or produced in the atmosphere through chemical reactions. As you can see, this reactor is a very complex system because there are so many different inputs coming from very diverse sources undergoing very complex chemical reactions. So you may understand why it's so challenging to diagnose the cause of air pollution. The good news is that the air quality in the US has greatly improved in the past few years. But there are still many challenges. Shown on the left is a figure to show the number of polluted days among 35 major US cities. You can see the number of polluted days decreased dramatically from more than 2,000 days to nearly 800 days in the past 20 years. This is indeed great improvement. But keep in mind, there are still 800 days with unhealthy air quality. We don't want any of them, right? If we take a closer look at this trend, the improvement in air quality slows down in recent years, which can alarm me. We also observe similar trend in many other cities, in many cities in the US. Shown on the right, this figure plots the ozone concentration from 16 different cities in the Southern California from 1980 to 2020. And each line represents one city. As you can see, they all follow a similar trend that, following a rapid decrease from 1980 to 2000, the improvement in the ozone remains stubbornly high since 2000. And ozone is stuck at a level that is higher than the air quality standard. And again, this trend is really alarming because why the progress in improving air quality is slowed down. This trend may suggest that our air quality policies may not be as effective as they used to be. So I'm interested in understanding the underlying mechanism for this trend. I want to figure out what is changing and what change can potentially cause this trend, and what changes could potentially cause our air quality policies to be less effective. So we live in a changing world. Many things are changing. To start with, the distribution of chemical emissions are changing. In the US, the emissions of SO2 and NOx has decreased dramatically in the past few decades. But the VOC, volatile organic compounds, decrease at a much slower rate. In this plot, you can see SO2 in red, NOx in blue, and the VOCs in black. The data shows from 2002 to 2018. And you can see the NOx VOC decrease much slower than the other two. And this disproportionate reduction in different chemical emissions could potentially lead to unexpected air quality issues. It's because our atmospheric chemistry is a very highly nonlinear system. Changing the concentration of one species could potentially affect the chemistry of another species. However, right now we don't have a comprehensive understanding about the chemical interaction between these chemical emissions. Besides that, the sources of VOCs are also changing. The VOCs comes from very diverse sources, such as vehicles, vegetations, or even the fragrance we put on. In the past, the VOC emissions from vehicle emissions has decreased dramatically thanks to the emission control technology. But many other sources are not well regulated. And a recent study pointed out that the VOCs from less regulated sources, such as personal care products, coating, or pesticide, these unregulated sources, are emerging as the largest source of urban VOCs. But right now, we don't know much about how much, what's the amount and the chemistry, how much of these emerging emissions are emitted, and the atmospheric chemistry of these emissions, because our past focus has been on these combustion emissions. Another thing that's changing is wildfires. This plot shows the area of burned that is increasing. This is mainly because of the historical fire suppression practices and the ongoing climate change. And wildfires emit tremendous amount of pollutants, and that really undermines our efforts to improve air quality. Besides these examples, many things are changing. In order to keep improving air quality, I think what we need to understand is the coupling of societal development, the corresponding change in emissions, the atmospheric chemistry of these emissions, and the environmental impact of such chemical processing. So eventually we can design effective air quality policies to improve air quality and to guide the societal development. But again, there are so many uncertainties in our understanding of the coupling between these elements. For example, sometimes we don't know what we put into the atmosphere. And sometimes this atmosphere is like a black box. We don't know the reactions going on. We don't know the chemical interactions between these different species. So the overarching goal of my research is to develop a mechanistic understanding of air pollution, to mitigate air pollution effectively, and to predict future air quality accurately. To achieve this goal, I will employ a range of tools, including laboratory study, field measurement, instrument development, and atmospheric modeling. So today, I would like to present 3 different air quality issues in different environments to illustrate the complexity and the diversity of our air quality issues, and more importantly, to illustrate what we can do to address these issues and keep improving air quality. So first, I will discuss how to reduce aerosol pollution from trees, and then I will discuss how do wildfire emissions and aromatic compounds impact air quality. So first thing I will discuss is how to reduce aerosol pollution from trees. This question may sound surprising to many people because how do trees make aerosol? So here's how. Trees emit a tremendous amount of volatile organic compounds, including isoprene, molterpenes, and many others. And these VOCs can undergo atmospheric oxidation and produce products with low volatility that can condense from gas phase to particle phase and make aerosol. Shown here is the SEM image of the organic aerosol produced from the oxidation of molterpenes. You can see the aerosol are roughly spherical and are about 100 nanometer in this study. But atmospheric aerosols can have even more diverse size and shapes. We call organic aerosol produced from the oxidation of biogenic VOCs as biogenic secondary organic aerosol, biogenic SOA. So biogenic means they originate from trees. Secondary means they are produced in the atmosphere rather than directly emitted. Organic aerosol means they are organic compounds in the particle phase, so biogenic SOA. So this is how trees can make aerosol. And based on my PhD study, we show that the biogenic SOA accounts for nearly half of the submicron aerosol in regions where there are a lot of trees. A long-standing question in our field is that how do anthropogenic emissions affect the formation of biogenic SOA? This question was proposed based on the observation that the biogenic SOA has a strong correlation with the CO. We know CO is from anthropogenic activities, and CO is not involved in the biogenic SOA formation. So this correlation may suggest that maybe some anthropogenic emissions affect biogenic SOA formation, and that interaction is reflected through CO as an anthropogenic tracer. But what are these anthropogenic emissions? And how mechanistically do they affect biogenic SOA formation? Those are the two central questions I'm trying to address here. And these questions are important because the answer directly determines the air quality policy regarding what species to regulate. The species of interest here is called isoprene, structure shown here. Isoprene itself accounts for more than half of the biogenic VOCs. And this is a map showing the isoprene emission in the US. And we can see the southeast United States is the hotspot of isoprene emission because there are a lot of trees. And in my PhD, I performed a 1-year measurement at 6 different sites in Alabama and Georgia, at both rural and urban sites. And the major instrument I use is called aerosol mass spectrometer, AMS. AMS can characterize the aerosol composition. And then I performed the positive matrix factorization analysis, PMF. PMF is just a statistical analysis that can separate organic compounds into different groups, representing where the aerosol comes from. This slide summarizes the source apportionment of organic aerosol in the southeastern United States based on my PhD work. So each pie represents one data set. Basically, that's a 1-month measurement at a specific site. All the summer measurements are shown on the top, and the winter measurements are shown on the bottom. And each color represents one source of organic aerosol resolved from the PMF analysis. So basically, for example, I resolved the organic aerosol from combustion, from biomass burning, from cooking, all over the southeastern United States. And then you can see the organic aerosol sources vary spatially and seasonally. And I can discuss this slide for hours. But in this presentation, I will focus on this blue fraction, which represents isoprene SOA. So again, isoprene SOA means the organic aerosol produced from the oxidation of biogenic isoprene. In summertime, isoprene SOA accounts for 18 to 36% of OA. And isoprene SOA is not resolved in winter because just trees do not emit isoprene in winter. And one striking feature we find about isoprene SOA is that it has a strong correlation with sulfate. Shown here are the time series of isoprene in blue and sulfate in red from ground measurement at 2 different sites. As you can see, they trace each other very well. And the correlation is about 0.8. And from the ambient measurement point of view, this is a really strong correlation. We observed the same result based on airborne measurement. Using the NOAA P3 aircraft and in the campaign called SUNX, we tracked the plume evolution. We tracked the plume evolution downwind of two power plants in Georgia, Sher and Harley Branch. Both are coal-fired power plants, but they have very different emissions of SO2. So Sher is very clean, has a very low SO2 emission. You know, SO2 oxidation produces sulfate, right? Sher is very clean and has very low SO2 emission, and you can see downwind of the Sher power plants, there's a small enhancement in sulfate between the plume and the background, and negligible enhancement in isoprene. In contrast, Harley Branch is very dirty, has a lot of SO2 emission, and as a result, we see substantial enhancement in both sulfate and isoprene SOA. So this is actually consistent with our ground measurement, that there's some correlation between isoprene SOA and sulfate. But why? Why would they correlate? Isoprene SOA is from trees, sulfate is from power plants. Why would they correlate? To answer that question, we need to go back to the lab and look at the formation mechanism of isoprene SOA. The oxidation of isoprene produces a compound called isoprene epoxidized, IEPOX. The IEPOX can partition from gas phase to particle phase, dissolve in particle water, undergo acid catalyzed reaction, and then react with nucleophiles to produce compounds that are a component of SOA. And this mechanism explains why sulfate correlates with isoprene SOA. It's because sulfate affects every single step in this process. So first, sulfate has a very large tendency to absorb water. So more sulfate means more particle water, which provides more medium to dissolve IEPOX. And sulfate also drives the particle acidity. So that will enhance this acid catalyzed reaction. Sulfate can also act as a nucleophile to directly involve in this reaction. So this mechanism explains why sulfate correlates with isoprene SOA, because sulfate affects every single step here. And the formation mechanism of isoprene SOA was discovered by Professor Paul Weinberg at Caltech. Without this detailed lab work, it's really hard for me to interpret the field measurement. So this made me realize the importance of fundamental lab study. So after graduation, I joined Paul's group as a postdoc. The major finding here is that regulating SO2 emission can reduce isoprene SOA. And this mechanism is implemented in many atmospheric models to evaluate the impacts of this mechanism over a wider spatial and temporal scale. So here's a figure from Morais et al., where they simulate a future scenario where the SO2 emission is reduced by 48% from 2013 to 2025. What they find is that as a result of SO2 reduction, the isoprene SOA, as in this black bar, will decrease by more than 30%. So this paper projects the change to 2025. Now we're already in 2022. So you may wonder, how do sulfate and isoprene SOA change in the past 10 years? Is this projection accurate? So here I make this plot to show the trend of isoprene SOA in blue and sulfate in red in urban Atlanta measurement from 2012 to 2020. As you can see, they both have a decrease in trend. So this is consistent with our projection. So yes, we are making the expected progress. To summarize, we found isoprene SOA is largely controlled by the anthropogenic sulfate. So a tighter SO2 emission regulation is an effective way to reduce isoprene SOA, which is supported by long-term measurement in the southeast in Atlanta. And also this study is truly based on the integrated approach of field measurement, laboratory study, and the atmosphere modeling. And one final comment I would like to make here is that our understanding about the aerosol sources and the formation mechanisms really depends on the instrument we use to measure the aerosol composition. The instrument I use here is the AMS. AMS can characterize the bulk composition, but it doesn't provide any molecular identification. So this really limits our understanding of the aerosol composition and sources and formation mechanism. So for example, there's a large fraction of organic aerosol that we don't know where it comes from. And to move forward, I believe future instrument development with improved chemical speciation, with improved temporal resolution and mass recovery, will provide a more complete description of the aerosol composition, based on which we can have a better understanding about aerosol sources and the formation mechanism. Just imagine if there's an instrument can measure every single molecule in the organic aerosol, then it becomes much trivial to tell where the aerosol comes from. So the first story has a relatively happy ending that we find a way to effectively reduce isoprene SOA. The next topic I want to discuss is not that very pleasant. I'm going to discuss about wildfires. Wildfires has been our news headlines so frequently in recent years. And you may recall some disaster fires in Australia, California, Amazon rainforest. And on the last day of 2021, Colorado just experienced the most destructive wildfires in the state history, and more than 1,000 houses were completely destroyed. And I know many NOAA and NCAR colleagues lost their houses, which is just horrible. And besides that, wildfires emit tremendous amount of pollutants, and that undermines our efforts to improve air quality. In 2019, I participated in a field campaign called FIREX AQ, led by NASA and NOAA. And many NCAR scientists are also heavily involved in this mission. This is an airborne study using the NASA DC-8 aircraft. And the aircraft is packed with more than 30 instruments, and they sample directly through the passenger window. And so we fly the aircraft can fly directly through the wildfire plumes for in situ measurement. So here's a picture of me sitting on the NASA DC-8 operating our SIMS instrument. And in FIREX AQ, we conducted 13 research flights and sampled more than nearly 20 different wildfires in the western US. Here, I would like to focus on the ozone formation wildfires. Previous studies have shown that wildfires can produce ozone, but the production amount is highly variable between different fires. Here, this slide shows the ozone formation and the function of smoke age from 3 different fires. And you can see sometimes the measurements are in the point, and the model are shown in the lines. Sorry, excuse me. You can see sometimes the model underestimates the measurement, but sometimes the model overestimates the measurement. So right now, an accurate simulation of the wildfire ozone is really challenging. I mean, this is a very complex system because different types of biomass burned under different conditions will lead to different emissions, which lead to ultimately different ozone formation. So it's really challenging to predict. So here, the question I'm trying to answer here are, what causes the variability in ozone formation between fires? And do we have adequate measurement and knowledge of wildfire chemistry to accurately predict the ozone formation? Before diving into these 2 questions, I want to give a very quick overview about how ozone is produced in the atmosphere. The key ingredients to produce ozone include volatile organic compounds, VOCs, oxidants, NOx, and light. The oxidation of VOCs by atmospheric oxidants, such as hydroxy radical, OH, will produce a proxy radical, RO2. RO2 can react with NO and produce NO2, and the photolysis of NO2 produce ozone. Besides reacting with NO, RO2 have other competing reactions which do not lead to ozone formation. Okay, back to FIREX. So here I want to show you a video taken by the forward camera of the DC-8. So you can see the fire starts from here, and the aircraft fly perpendicular to wind direction through the fire, and all these plumes are the aerosol emitted from the fire. Okay, so we fly perpendicular to the fire. As we approach, you can see we're entering the fire now. The visibility decreases. And then we are going through the fire, still in the fire, now in the thickest part of the fire, but still in the fire. It's pretty wide. Now we are almost, now we are out of the fire, finally. So this is really wide. This transect is about 20 kilometers. It's a very intense fire. And after cross this plume, we'll make a U-turn and cross the plume again at different downwind distance. So the typical sampling strategy is this ladder pattern, which involved several crosswind transects at different downwind distance. And a widely used method to analyze such measurement is the Lagrangian framework. So basically in this framework, it's assumed that all these transects sample the same plume parcel over time. And then the transect average properties can be plotted as a function of the smoke age to study the plume evolution. But in reality, it's really challenging to sample the same plume parcel over and over again, right? It's just because aircraft moves much faster than the wind. Let's imagine it takes a plume an hour to move from location 1 to location 2, okay? In order to sample the same air plume parcel, after the aircraft go through location 1, it needs to wait for an hour and then come back at location 2, right? But in reality, after sampling location 1, the aircraft spend like less than 10 minutes to make a U-turn and sample location 2 right away. So in other words, these plume transects are not sampling the same smoke, right? This may be one reason why when you compare these successive transects, the data is so noisy. And just because the fire conditions change dramatically over time, so what you are sampling at location 1 and location 2 could be totally different things. I'm not saying that the Lagrangian framework is wrong. I just want to point out we need to understand the uncertainties behind this analysis. So in this study, we developed a novel analysis based on single transect to study the plume evolution. So instead of comparing successive transects, this analysis examines the plume composition across each individual transect. The idea is that the aerosol concentration is higher in the plume center than the plume edge. And aerosol diminishes sunlight and makes the aerosol center darker than the edge. Just to recall the video I showed you 2 slides ago, the plume center is really dark, right? And as a result, there is less photochemistry in the plume center than the plume edge. So this naturally provides a different extent of photochemistry across each transect. To show you an example, here this plot shows the time series of the sum of ozone and NO2 in black, and OH exposure in blue as the aircraft enters and exits the plume. So plume edge, plume center, and plume edge. OH exposure is a measure of the chemical aging. So larger OH exposure means more photochemistry, and the plume is more aged. So we can see here the OH exposure is higher in the plume edge than the plume center. As a result, the sum of ozone and NO2, which are produced from photochemistry, are also higher in the plume edge than the plume center. And most importantly, in each transect, the aircraft samples the plume, sample the smoke that are emitted at similar times. So basically, all these measurements within each transect have similar initial fire condition. And the difference we see here are largely because of the chemistry instead of emission. So in other words, we can treat each transect as an individual event to study the plume evolution. And for each plume transect, we derive this, quantitatively, we derive this expression to calculate the OX production across each transect. I want to note that here I study OX, which is the sum of ozone, NO2, PAN, nitric acid, and particle nitrate. I mean, OX is selected here because it accounts for the rapid interconversion between ozone and other OX species. And the OX production is expressed by the product of 3 terms: the VOC reactivity in blue, and the fraction of RO2 that reacts with NO in red, and the OH exposure in purple. These 3 terms are related to the key ingredients in ozone formation, which are VOCs, NOx, and oxidants. Using the extensive measurement on the NASA DC-8 aircraft, we managed to experimentally constrain each terms. And this is a critical aspect of our study, but limited by time, I will not go into the details here. In addition to calculate the OX production based on the VOC, RO2, and the OX exposure, we also directly measure the OX production across each transect. And we can compare the measured and the calculated OX production across the same transect. And this comparison helps to evaluate how well we understand this wildfire ozone chemistry. The comparison is shown in this plot. The y-axis is the calculated OX production. The x-axis is the measured production. And you can see each data point represents one transect. And the gray circle represents the uncertainty. And you can see overall, the calculated and measured OX agree within like 10%. And this agreement suggests that the majority of VOCs contributing to wildfire ozone have been captured in the FIREX AQ campaign. And this agreement also suggests that there's no apparent missing source or missing sinks of OX in the wildfire plumes. And these insights enable us to diagnose the potential reasons for the discrepancy in previous studies. So first, I think the discrepancy between the measure and the model in previous studies, the most important uncertainty is this Lagrangian framework, because each transect are not the same plume parcel. They could be different things because the fire condition changed so dramatically over time. And secondly, many critical VOCs, such as the oxygenated aromatics and furans, are not captured in previous studies because of analytical analytical limitations. In FIREX, the NASA DC-8 carries an extensive suite of instruments that characterize a wide range of VOCs. And lastly, the oxidation chemistry of many VOCs has many uncertainties in previous studies, but that has been gradually addressed in the recent years, which I will discuss in the next topic. But as you can see, our prediction about ozone has greatly improved over the years. So from 2019, this is two studies by my colleagues Mike Hogan and Mike Robinson, using recent years' data and measurement. You can see the model is getting better after accounting for the more VOCs and their chemistry. To summarize, I think a proper analysis method, a comprehensive measurement, and the accurate chemistry of these emissions, the combination of these three components is really critical to address this puzzle. And based on the extensive examination of VOCs, NOx, ozone, and OH, we provide a framework to describe ozone chemistry in wildfire plumes. So wildfires emit a multitude of species, including NOx, nitrous acid, also known as HONO, and an enormous diversity of VOCs. In the near field, the OH produced from the photolysis of HONO initiates the VOC oxidation. The reactive and the primary VOCs, such as alkenes and furans, are oxidized, and this oxidation proceeds in the presence of abundant NOx. So the majority of RO2 reacts with NO and leads to efficient ozone formation. But after just a few hours, the ozone chemistry slows down, as represented by the narrow arrows on the right plot of this figure. This is because HONO has been largely depleted, leading to reduced OH concentration. The NOx concentration also decreases substantially because of dilution and chemical loss. And as a result, only a small fraction of RO2 reacts with NO. However, the VOC concentration remains elevated. This is because the oxidation of these primary VOCs produce a lot of small oxygenated VOCs, and that sustains the VOC level. So in summary, just after a few hours, ozone formation slows down because of a lack of NOx. And this brings up a very interesting question. What would happen when a VOC-rich, NOx-depleted wildfire plume mixed with an urban plume that has a lot of NOx from vehicle emissions? Our mechanism suggests that ozone formation will resume. Is that true? A study by Bray et al. Compared the ozone concentration for smoke-impacted days and smoke-free days for 500 cities in the US. And they found that, as shown in this histogram, when impacted by wildfire, the ozone concentration is enhanced in both rural sites in blue and urban sites, as shown in the red. And what's more impressive is that the ozone enhancement is larger at urban sites with higher NOx than rural sites with lower NOx. So basically, this is consistent with our hypothesis that adding NOx to the wildfire plume will make more ozone, and that will degrade the urban air quality. And thinking more broadly, the impacts of wildfire emissions, the impacts of wildfire on the air quality really depends on the environmental condition of the downwind community, which could be very different from different locations. So in order to accurately predict the impacts of wildfires on air quality, it really demands an accurate understanding of the underlying chemistry. Another aspect worth further investigation in terms of wildfire chemistry is the fundamental chemistry of several traditionally overlooked VOCs. Such here is the aromatics and the furans. In wildfire emissions, aromatic and furans together account for about 1/3 of total VOC emissions. And there are limited number of studies on the fundamental chemistry of these two classes of compounds. I mean, aromatic chemistry was the focus of our community like 30 years ago. But later, our community shifted focus to other topics and leaving many outstanding questions unsolved. Besides wildfires, many anthropogenic activities emit a lot of aromatics. And in fact, the aromatic emission in many countries are rising. Shown on the bottom left is a figure that shows the emission of several anthropogenic VOCs in China from 1990 to 2017. The total aromatics, as shown in this blue shade, are on the rise. And this rise is because of solvent use and industrial processes. Recall in the introduction, I mentioned that the VOC sources are changing. This is another example to illustrate that. And on the right, I show the toluene concentration in the South Korea Peninsula from the NASA FIREX AQ campaign that I'm working on. You can see near many major urban cities, the toluene concentration can reach up to 100 ppb. This is really high. As a reference, the toluene concentration in Los Angeles, which is one of the most polluted cities in the US, is less than 1 ppb, right? So this can reach 100 ppb. All these observations really motivates me to understand the fundamental chemistry of these aromatics and furans. So lastly, I would like to briefly discuss how do aromatic compounds affect air quality. So aromatics contains a wide range of compounds. And here I would like to start from the simplest aromatics, benzene. I treat benzene as a model molecule. I want to understand its chemistry first, and then provide insights into the chemistry of more structurally complex aromatics. To study the benzene chemistry, I performed a set of laboratory experiments in a 1 cubic meter Teflon chamber. I inject benzene, OH radical precursor, and NOx into the chamber, turn on the lights to mimic the sunlight and the atmosphere chemistry. The idea of this type of experiment is that we use a suite of instruments to measure the oxidation products. And then we use the time profile of these products to retrieve useful information, such as the reaction rate constant or the product yield. And based on this information, we can develop a mechanism. But the challenge here is that there are very complex series parallel reactions produce a number of compounds, which are sometimes very hard to measure and quantify. The major instrument I used in this study is a chemical ionization mass spectrometer, CIMS. CIMS is a very widely used technique in our field to measure for fast measurement of a number of atmospheric species. And here I use Cl3O as region ion to measure oxygenic compounds such as alcohol, nitrate, acid, and peroxide. I also use NO+ as a reagent ion to measure less polarized compounds, such as benzene and aldehydes. And one major improvement we made at Caltech is to couple the SIMS to a customized designed gas chromatography, GC. This is a perfect marriage because one major shortcoming of mass spec in general is that it only measures the mass to charge ratio, and it cannot separate isomers with the same chemical formula. But the GC can separate isomers. So by coupling the GC and SIMS together, this issue is addressed. And the customized design GC at Caltech use a low pressure technique and inner surface to avoid unwanted decomposition reactions. And that significantly improved the transmission efficiency of oxygenic compounds. And that is a major improvement. And besides that, the customized GC we built is very compact. So here's a picture showing the GC I built. It's only 9 inches wide and 14 inches tall and only 3 pounds. It's very easy to move. And I would like to use this slide to illustrate the unique measurement capability of this GC SIMS. So for example, in benzene oxidation, I'm interested in the yield of this hydroxynitrate with the chemical formula C6H7NO5. And shown here is a gas chromatography measured by the GC SIMS in the benzene oxidation with this chemical formula C6H7NO5. And each peak here represents one isomer, has this chemical formula. And based on a careful examination, we find that only the peak eluting at 1030 seconds match the structure of these compounds. All the other peaks are something else, okay? Without the GC SIMS, we would not know this isomer distribution. And what SIMS reports are the sum of all these peaks, which is used in the literature to report the yield of these products. And that leads to an overestimation of the yield and an inaccurate mechanism. So this just an example to illustrate this GC SIMS has a unique isomer-specific measurement capability, and that is really critical to develop an accurate mechanism. Using this state-of-the-art instrument and a set of laboratory experiments and quantum chemical calculations, I managed to develop a detailed and quantitative mechanism to describe the benzene oxidation. This looks a rather simple slide, but there are more than 60 experiments behind it. So instead of going into all the details, here I will only present some key findings and discuss how this mechanism can address some long-standing questions. In the atmosphere, benzene dominantly reacts with OH and produces a product called phenol with a yield of 50%. And phenol is very corrosive to skins and eyes. That's a compound that we do not want in the atmosphere. Then I found that the current mechanisms, such as MCM, misassign 10% carbon into a product that doesn't exist. So in previous studies, all the compounds they measured cannot match the input carbon. For example, maybe 10% or 20% carbon are missing. The previous study assigned this missing carbon into a hypothetical compounds as a placeholder. But based on a careful examination, we find this product has a very negligible yield and not produced in the benzene oxidation. Instead, I also identify new reaction pathways, which lead into several reactive aldehydes, and that likely account for this missing carbon. So looking at this C6H7O4 alkoxy radical, this aldehydic hydrogen can undergo a shift, okay, from here to here, and then keep decomposing to different aldehydes. And I want to know that the fraction of missing carbon increases with the size of aromatics. For example, in xylene oxidation, more than 30% of carbon is not accounted for. And I believe this newly identified reaction pathway also occurs in the xylene oxidation. And these products likely account for that missing carbon. Or this mechanism will help to achieve carbon closure in other aromatic systems as well. The last major finding is that the radical recycling is more efficient than currently than expected. When RO2 reacts with NO or HO2, they largely recycles into NO2 or OH, rather than produce a stable, closed-shell stable products. So the implication is that the benzene oxidation will likely produce more ozone and more OH, more radicals than currently thought. And this is likely true for other aromatics as well. The reason we need to develop this detailed mechanism is to evaluate the impacts of aromatic compounds on the atmosphere composition. So Kelvin Bates and many others, and co-authors, implement our new benzene mechanism as well as many recent findings about aromatic chemistry into GeoSCAM, which is a model to simulate global atmosphere composition. They compare the simulation, one simulation with aromatic chemistry, another simulation without aromatic chemistry. The simulation showed that including aromatic chemistry can increase the OH concentration by up to 25% in polluted regions such as China and the Northeast US in wintertime. Including aromatic chemistry can also increase ozone concentration by up to 5 ppb in some regions in wintertime. Besides ozone and OH, the simulation also showed that aromatics are an important source of small oxygenated organic compounds, such as glyoxal, methyl glyoxal, and formic acid. The reason I mention this small oxygenated compounds is that they now can be measured from space using satellite. And it's a very active and promising area to combine satellite observation and modeling result to infer anthropogenic emissions and air quality. But what I want to see here is that interpreting the satellite observation really demands an accurate understanding of the fundamental atmospheric chemistry. Okay, just to summarize, the overall goal of my research is to develop a mechanistic understanding of air pollution, based on which we can mitigate air pollution effectively and to predict future air quality accurately. In the past 45 minutes, I showed 3 different air quality issues. So first, I showed that isoprene SOA is regulated by anthropogenic sulfate, and reducing SO2 is an effective way to control the isoprene SOA. The second story focused on wildfire chemistry, and the key finding is that wildfire ozone formation is limited by NOx, and when NOx-limited wildfire mixes with urban plume with a lot of NOx, ozone formation will resume, and that will degrade the urban air quality. And lastly, I briefly discussed the aromatic chemistry, benzene chemistry, and using the state-of-the-art instrument, I managed to develop a detailed chemical mechanism, and that is really critical to evaluate the impacts of aromatics on the atmosphere composition. And finally, I want to say that we live in a changing world. The threats to our air quality are constantly changing. But after we understanding the coupling of societal development, the corresponding change in emissions, and the atmospheric chemistry of these emissions, we will be able to develop a prognostic ability to prepare for future environmental challenges and keep improving air quality. So with that, I would like to thank my advisors, Sally, Paul Weinberg, and Carsten Warnicki, for their support through the years, as well as the many collaborators and colleagues in the past, as well as the funding agencies. And thank you for your attention. I can take any questions now.
Thank you so much for the very good talk. Let's see if we have some questions from the room. Yes, I'm gonna get there. You guys, you go all the way on the back.
Hello, thanks for the talk.
Thank you.
My question was, when you're talking about how the sulfate will affect isoprene SOA formation, presumably the isoprene will get oxidized eventually, right? So to what extent is that really SOA prevention versus SOA deferred?
Oh, I see. So without sulfate, isoprene will oxidize, but that will produce less SOA. compared to in the presence of sulfate.
Oh.
So isoprene SOA yield. So SOA yield of SOA yield of isoprene oxidation is lower without sulfate. Does that answer your question?
Yeah.
Okay, thank you.
So in one of your earlier slides, you showed that the trend in ozone was going down and then it leveled off. And you put out a bunch of different mechanisms how that could be affected via reducing SO2, but wildfires tend to increase ozone. So in that figure, were you talking about just a given region, or was this for the US in general? I don't remember what the slide.
Yeah, I see. Come on. I guess you're referring to this slide.
Yeah. Uh-huh.
Yeah, so this slide is only for the 16 cities in the Southern California.
Okay.
And this trend is the most prominent in that region. And I think one running hypothesis is that we're in a different regime of the VOC NOx,
Okay.
the isotopes now. And in the past, NOx decreased much faster than the VOC.
Uh-huh.
So that caused some.
And this is a region where you don't have many wildfires.
Oh, there's a lot of wildfires
There's
in
a
California.
wildfires.
Yeah.
Okay.
I think wildfire also contribute to these trends to some extent.
Okay, I got confused. I was thinking the wildfires would increase ozone. But it depends on the background NOx, I guess.
I
all
think
that
so.
Stuff. Yeah.
Yeah.
Okay.
Yeah, I think that's an ongoing research question and very important. Thank you.
Is there anything from Slido?
Simply because I'm a modeler, and that was a really excellent talk. When you show the simulations on a global scale, how ozone changes when you include the aromatic chemistry, did you only change benzene chemistry in there, or did you apply the same mechanism for all aromatics? And as a follow-up question, how would ozone change in summertime?
Right, great question. So that simulation compares all the aromatics, not just benzene, all the aromatics. Okay, that's the first part of your question. And secondly, that's the figure I showed is for winter. For summer, the effect is smaller because in summer they're more biogenic, makes a more important role there.
Thanks.
Yeah.
Question about isoprene and SO2. There is also, so where is that aerosol coming from to begin with? Because I'm probably very biased because I've studied a lot boreal forests, and there we see nucleation with sulfuric acid and oxidated monoterpenes. So there is no aerosol to begin with, and then because of sulfuric acid initiating nucleation, then there is SOA, I will call it. But here in the US might be different.
Yep.
Is that right? And how is that different from a boreal forest, if you're familiar with the boreal forest?
So the data I show here are from the southeastern United States. Is not as clean as a Amazon forest or boreal forest. So the sulfate mainly from power plants. So you can see these spikes are from the nearby power plants.
You're showing aerosol in microgram per cubic meter.
Right.
And my question will be, is that an increase in mass of pre-existing aerosol, or is that new aerosol that wasn't there before?
Right. So here, I think the mechanism, there is some existing aerosol with sulfate inside that. And then I epox partition from gas to particle phase. So this doesn't touch the original aerosol.
Okay.
Yeah.
Okay, no more questions. I will thank you once more.
Thank you.
And thank you all the audience. Let's thank Lou with an applause. For the people in the room, people in the streaming, for following our seminar series. See you next time.